it won't happen now that I'm about to say it, but because the people on the roof, I lost my Zoom contact with my previous class for about 5-10 minutes. So if suddenly I just mid-sentence disappear on you, will you just hang around? I will get back in. It's not that they're cutting the cables, and it might not be anything to do with them. That's why I'm saying it probably won't happen now. But I think when you have those big electric things, they can sometimes cause little spikes, and maybe that's what it was, and maybe not. So we are finishing off chapter 10 today, and there are only 6 questions, and we are going to take the idea of getting a confidence interval for a single proportion, which is what the early one is, and kind of up it to calculating the a confidence interval for the difference in 2 proportions. Right? So imagine that you've got 2 groups. So we've got Scots people, we've got an Americans. And in the Scottish group, I take a sample of 250 people. And in the American group, I choose, well, I don't know, say 400 people. Right? And we ask them the same question. And what we're going to do here is we're going to see if there's any detectable difference between the 2 groups. So that's one of the reasons you would do this, right? So that's what we're going to do. And so I asked the first group, the Scotsmen, how many of you like whiskey? Because we're in a whiskey world. And 100 of them said they liked whiskey. And we went to the Americans sample of 400, and we said, how many of you liked whiskey? And 120 of them said they liked whiskey. So far, so good. Now, couldn't I find a 95% confidence interval for just the percentage of all Scots people who like whiskey? And couldn't I do a separate one for this guy, right? But what we're going to do, in fact, is we're going to find a 95% confidence interval for the difference between them. So while I'm at that, this guy here is, I believe, 0.4. I made sure they were nice. And this guy here is 0.3. So if you look at it superficially, would you agree that the Scots like whiskey more than the Americans, right? 0.4, 0.3. But we also know from experience that when you take a sample, there's a lot of variation. So couldn't this just be a rather unusual large answer? And couldn't this be a rather unusual small answer? And the truth is that Americans actually like whiskey more than Scottish people, right? That could happen. So what we're doing is we're going to take the difference between the 2 and then a 95% confidence interval in this case. And then once we've got that interval, we can then decide whether or not there's any significant difference between these 2, right? Or whether it could just be randomness, and yeah, none to see here. And the formula is this guy here. So if you want to find a 95% confidence interval for the difference in 2 proportions, it's P1 hat take away P2 hat, right? First population, take away the second. Oh, and by the way, when you're doing the homework questions, because I get caught out, the story might say Scottish people did this and American people did that, but later on, they want this guy to be American and they want this guy to be Scottish, right? What on earth they did that for was annoying, but be careful, right? Look at who they're calling P1, right? P1 is Scottish people, right? P2 is American, or vice versa. Right. Plus or minus, do you recognize the 1.96 guy? In fact, if I rub that out, isn't that essentially the formula we were using yesterday? Now, we are going to finish with the standard error of P1 hat take away P2 hat. Now I'm going to move this piece of paper over, because the formula for calculating the standard error is this ugly guy. Now, it's not as weird as it looks. If I cover that up, isn't that the formula for the standard error of P1. And if I cover this up, isn't that the standard error for the other guy, P2? So can you see all they've done is add them inside the square root. So it's not totally weird, but it is messy, right? So let's calculate the standard error in this story then. The standard error for the difference between the two is the square root of P1 hat, which is, oh, let's put the formula in. P1 hat, 1 minus P1 hat, all over N1. P2 hat, 1 minus P2 hat, over N2. Now I can put in the numbers. P1 hat is 0.4. Take that away from 1, you get 0.6. And there was 250 Scottish people asked. And then you do the second one. And in the second one, you have 0.3, that's P hat 2. If you take that away from 1, you get 0.7. And we asked 400 Americans. And as ugly as that looks, actually you can do it in one go in your calculator. So I guess that's something. So here we go. Square root of 0.4 times 0.6 divided by 250 plus 0.3 times 0.7 divided by 400. And do you notice you don't need brackets, which is nice, because some of them you have to do brackets to make sure it does it in the right order. If you just type it in, it works. And so the answer that we get here is 0.039. Well, that's to 3 decimal places. So back to my formula for the 95% confidence interval for the difference in 2. And P1 hat is 0.4. P2 hat is 0.3. Plus or minus 1.96 times 0.039. Right, if you take those two guys away, you get 0.1. Plus or minus, let's do that in the calculator, 1.96 times 0.039. And the answer I get is 0.0766. Now, if you subtract that, you get 0.024. And if you add them together, you get 0.176. And that's the answer as a proportion. If you want the answer as a percentage, it's 2.4% up to 17.6%. So the difference between Scots and Americans' preference. Do you notice that this interval consists of nothing but positive numbers? What that means, and how we can interpret that is, that means that the first thing is bigger than the second. In other words, this is evidence that Scottish people drink whiskey more than Americans, right? Because the difference is positive, right? So if P1 take away, the math of it is, if P1 take away P2 is a positive number, mathematically, isn't that what you're saying, right? That P1 is bigger than P2. What would you do if the interval was all negative, right? Suppose it was negative number to another negative number. What would be the conclusion this time? When they're positive, the first guy is bigger than the second. But what happens if the interval has nothing but negative numbers in it? What do you interpret that to be? Anyone?
The first one is smaller than the second one.
Yeah, that'll work. First one is less than the second. You could have said the second one is bigger than first, but that's the exact same thing as what you just said. So that's how you could do it. But what do you do if this happens? So the fancy jargon for this is that the interval contains 0, right? So it's a negative number and it's a positive. So it's like negative this guy, positive that guy. Now, in that case, your conclusion will be that you cannot tell any difference between the two. We're not saying that they drink exactly the same amount of whiskey or they like the same amount of whiskey. All we can say is there's not enough evidence one way or the other to say one is bigger or less than the other one. Does that make sense? So if a difference, if the interval has a 0, if it contains 0, your answer is going to be not enough evidence to detect a difference. If it's all positive, first guy bigger than second. If they're all negative, first guy less than second. Yes, question? No, thought someone was trying to say something. Are we cool with that? And my second example. Let's do a clinical trial one, which is a big usage of this technique. Let's suppose that we have the old cancer treatment, right? And we have the new cancer treatment, right? And in the old cancer treatment, they took a sample of 1,000 people and 900 of them survived. So that's a really effective cancer treatment, isn't it? Now, when they do cancer, how am I phrasing this? Success is people alive, but people will die. Everybody's going to die. So they tend to actually just have figures like people who are still alive 10 years later, right? Because some people are going to die anyway. And so you can't just say, well, the treatment finished and they're still alive, because that's not really realistic, right? Don't you have to wait at least a year or two in case the cancer kills them, right? You're not, you know. So when they talk about success, 90% might well mean that 90% of the people are still alive.
Yeah, it's dead, huh?
After a certain amount of time.
Sorry,
Okay.
Bubba.
Right. Now, there's a new treatment app. And 500 people, I'm going to just do a little changey thing here. So you want to answer, hit spacebar. Right, so back to where it was. Oops, just getting background. Come on. Here we go. New cancer treatment. 500 people take it. Oops, I better put the number in first. $460. Right, looking at the raw data here, would there be evidence to say that the new drug might be even more effective than the old one? Right. But couldn't that just be randomness, right? So we are going to do a confidence interval for the difference, and I'm going to just pretend, and then we'll see what it is. I might get an answer that looks like this. The difference between them is negative 0.01 to negative 0.017, right? Something like that, right? Make that a 9, make that a 7, right? Everybody is negative. When everybody is negative, doesn't that mean this is smaller than that or that's bigger than this? That is what you want, because if you've got that, haven't you now got evidence that the new drug is doing a better job, and you probably want to, you know, put it out in the market because, you know, okay, an extra 2% might not mean a lot to you, but to the people who've got that cancer, you know, it's life and death, right? It's important. Of course, you might get right, one of those contains zeros, won't you? And if that interval happens, won't the conclusion be we can't tell the difference, right? That one might be better, it might be worse. Couldn't this be a little bit lower than normal? Couldn't this be a little bit higher than normal? And they could even switch around, right? So no evidence, we have evidence. So let's see what we get. Since this is a cancer treatment one, why do you think I'm going to do a 99% confidence interval rather than one of the other two? Why should you choose a 99% confidence interval when you do something that's serious rather than people who drink whiskey? So if you get it wrong, you know, nobody's going to die, right? I kind of did the answer there. If you get it wrong, somebody could die. Don't you want to be really
absolutely sure the information's on your side?
You want to be sure when you say this drug's better than that it truly is. Because if it's not, aren't you actually giving people an inferior treatment than they would have got if you just left them alone with the old one? So on a 99% one, it's P1 heart, take away P2 heart, and give or take 2.58 times our standard error filler. And P1 is 0.9 and P2 take away is 0.92, and it's going to be 2.58 times the big ugly guy, and that's going to be what, a 0.9.1 over 1,000 plus a 0.92 over a 0.08 over 500. So I'm just going to do that guy on its own, see what we get. So it's the square root of 0.9 times 0.1 divided by 1,000 plus 0.92 times 0.08 divided by 500. And I have 2.58 times 0.015. And this guy is negative 0.02. So we have negative 0.02, give or take 2.58 times 0.015. And this answer is 0.039. Right. If you take these guys away, you get negative 0.059. But if you add them, you get positive 0.019. Would you agree this is inconclusive then? The interval contains 0. Inconclusive. So if you're the pharmaceutical company and you've done this clinical trial and you've spent a lot of money doing it, and this answer comes up, the FDA will not allow you to use the new drug. There are a couple of rules that the FDA, right, the people who are in charge of, in America at least, everything to do with medication and treatment. One of the rules they have, the first rule essentially, is it can do no harm. So you actually have to do a clinical trial where you test to see if there's any horrible side effects, right? Whether, you know, people have heart attacks with the treatment or whatever. So that's the first hurdle. Now, once that's gone, their second rule is that the new drug must be better than the old drugs, right? They're not going to allow you to just bring a new drug on market if it's not as good as 0.9, right? And that's the second major rule. So pharmaceutical companies have a lot of money tied into this. So you can see that they want this to be significant, right? So the FDA have rules about how to conduct clinical trials to stop them, you know, pushing the evidence on their side so that they'll get their medication prevented. And for instance, one of the things they almost always try and do is make sure it's double blind. So nobody knows what treatment you're getting. So if it's a cancer treatment and it's just a pill, the doctor that's your normal doctor doesn't know if you're getting the usual pill or the new one, right? And the people who are recording, you know, people who died, people who lived, they don't know what's going on either, right? They're just collecting the data. And the person who collects the data is not the pharmaceutical company. for obvious reasons. It has to be an independent person, right, who's got nothing to do with them that does it. Actually, it's typically the FDA who do it, right? They collect the data and they say, okay, it worked, or ain't going to happen. And when you get a new drug, if this one did work, that one might cost you, I don't know, $5 a pill. Won't that cost you $50 a pill? They don't get rid of the old drug, right? That's generic, right? That's still going. But if you want to get the new treatment, don't you very often have to pay a lot more money? I can tell you right now, one of the medications of the many that I get to take, when I first got it, it cost $700 per month for one treatment. Thankfully, my insurance paid, what, 80% of it, 8% of it, but it's still a lot of money, right? Now that drug has gone generic, I think it cost me about $1. So you might think that's a bit of a drop. And I'm not really a fan of pharmaceutical companies, but there is sort of some evidence to prove why they do it. They have so many failures and so few successes. Don't they have to pay for all the failures by charging a lot of money for the few successes? And so they get, I don't know what it is in America. Is it like you get 10 years where you can be the only guy in town and then it goes generic? And so for those 10 years, you know, they've got, they'll make a wad of money. But that's to pay so that they'll have enough money to do new research on new drugs and fail 10 times, losing millions of dollars on each failure so that the one success, hopefully, that they get moves on. Now, I'm not 100% convinced by that argument, but I could sort of believe it, perhaps. Well, that is pretty much the process, right? So let's show you, to finish with, how WebAssign makes your life hard. As you know, WebAssign's not going to always give you a question as clear, hopefully as clear as my two stories were, right? But they're essentially the same, right? And let's start with question 1. Can I make that bigger? Let's make this bigger. That'll make that bigger. And I don't want the answers because that's very distracting. Okay, here goes. 1, 2, 3. 3's too much. Okay, 2. Question 1, in an ongoing nationwide survey, a question asked is whether the respondent favors or opposes capital punishment. So in the year 2008, 635 people out of 1922 were opposed to, you know, being hanged for murder, right? Capital punishment. And they even tell you what p-hat is, so you don't even need to calculate it. And then in the year 1993, 335 out of that number, which is that number, right, has gone down. And if you do the first one, take away the second one, they even subtracted the answer from you. And they even found the 95% confidence interval for you. So you didn't need to do any in the number crunching, right? Here we are, I'll tell you. So now we're going to take this table and pretty much use it. What proportion from 2008 were opposed to the death penalty? The answer is simply 0.330. That's all I did. Now, what proportion in 1993? 0.236. What was the difference between them? The difference between them was 0.094. This is almost not a question, isn't it? It's just like, can you read numbers? That's really all it is. Now, write down the confidence interval, right, as it's given in the output. Well, it's given in the output as 0.064 to 0.125. That wasn't too hard. And then it says interpret it. Okay, so, well, I'll let you pick it. I'm never quite sure with these guys because I end up picking that one and the answer's that one. But since there's 5 guesses, won't you get it right eventually? And then you can say, oh, okay, that's how they phrase it. Now, which one of these many weird looking formulas is the one that you would be using? And oh, by the way, see that little Z star thing that they've got there? That's just a placeholder for the 1.645, the 1.96 or the 2.58, right? So that's an even more general version of mine. Okay, top to bottom, number 1 to number 5. Which one is it?
Four.
Which one of these is our formula, the one that we would be using to calculate the 95% confidence interval?
The fourth option, like she said earlier.
Oh, I thought you said what, Maggie? Did you say 4?
No, I said 4.
You did. My hearing. I'm wrong. If you then take this, one of these calculations be the real calculation that you would do, and can you just basically figure out who P1 is and make sure that's P1, figure out what 1 minus it is, and then take it over the other number. So if I just go up here, I want a 0.3 and a 1922 guy. So I want a 0.3 and a 1922 guy. I want a 0.3 and a 19. Oh, I believe it's that one. Okay, in that question, you really didn't do anything. Didn't they do it for you? And you just had to pick out the bits that were going to work. Right. Now, in this one here, we've got a real story. And you can use salt to check it if you like, but I'm not going there. I might do it at the end, but I want to see how much time we've got. So a study was done to determine whether there is a relationship between snoring and heart disease. Among that number of snorers, 85 had a heart disease, and under that number of non-snorers, they had a heart disease, right? So you have 2 groups, snorers, and the p-hat is percentage of people who have heart issues, non-snorers, percentage of them, right? Wouldn't that be like the, well, isn't that the same 2 examples I just gave? Isn't it population 1, population 2? Wouldn't you go through all that stuff? And then you just write your answer down. I'm going to make up an answer. I'm going to make it 0.05 to 0.07. Oops, no, put it in the right place. 0.05 to 0.07. Now, if that was the real answer, right? Would that be evidence that snorers have more heart attacks than non-snorers? Is P1 bigger than P2 if everybody's positive? Yeah. So if that was correct, you would say yes, but notice you'd say yes because it does not cover 0. Right. When they say covers 0, they mean the interval has 0 inside. When they use the phrase does not cover 0, they mean the interval doesn't have 0 in it, right? 0's not in the interval. That's the phrase that he is. Does that question make sense? No, even though we don't do details, right? Now, in this big long one, in a study, investigators surveyed individuals by telephone about how often they get tension headaches. One response variable that was measured was whether or not the respondent had experienced an ETTH in the prior year. Now that's a headache pattern where it occurs less often than 15 times a month. Okay, if you're into nursing, you're into that. I'm just going to say they got a headache, right? Evidently. Don't they do that in medicine? They don't say you've got a broken arm. Don't they say you've got a broken left tibula or something? And then you say, what's that? Oh, you broke your arm. Why didn't you just tell me I broke my arm out? You know, whatever. Anyway, what are the numbers we're going to be dealing with? Well, we have two populations. One is the 18 to 29-year-olds, and there was 1650 of them. And out of that 1650, that many had headaches. Now, the other group is the 30 to 39-year-olds, and there was 2,000 in that group, and 991 of them had headaches. Can you see the two populations, the P1 hat and the P2 hat, right? And then once you've got that, can't you put the P1 hat, the P2 hat, the difference between them, and then do the confidence interval, and then pick one of these, and you're finished. I know I skimmed through that, but isn't that kind of like the two stories, right? Population one, population two. Here is the same information given in a table format. In a certain survey, a question asks whether you favour punishment again, right, the death penalty. And in the year 2000, 791 out of that said, yep. And in this year, that one. And they even told you the difference. So if you look at these numbers here, shouldn't you be able to calculate the standard error? It's going to be the square root of P1 hat, which is this guy, times 1 minus this guy, divided by that number there, plus P2 hat, which is this guy, times 1 minus this guy, divided by that sample size. And you'll get whatever the answer is. And then a 90% confidence interval. Now, I hope this is okay. I feel I'm talking through things without doing things, but I'm hoping that you know what I'm saying, right?
Is that so? For that one, let me see if I'm just understanding it correctly. We would take that number right there and times it against the 90% interval. Would we?
Well, let me show you. I think maybe this is a good point for me to kind of make this more specific, because you can be too general. I've lost my little guy. There he is, he's up there. So I'm going to write down that table again and show you how you would use it to build a 90%, in this case, a 90% confidence interval. So we had the year 2000. This is me copying the table. And with the year 1993. And the guy they're calling X is just the number of people who said, yeah, I'm in favor of it. And N is the sample size, which in this case was that. And then they told us here what they're calling the sample P. That's really just what P hat is, right? So this one here is 0.318. And then the 1993 data, 337 out of 1488 were in favor of it. And the P hat for that one is 0.226. And they've got a guy called P1 takeaway P2. I actually put hats on them, but they didn't. And they told you that that number was 0.092. So if you think of this as being P1 hat, and this is P2 hat, P1 hat takeaway P2 hat is 0.318, takeaway 0.226, which happens to be that number. They just did the calculation for me. Now, the next question they said is, tell us the value of the standard error. And that's going to be a big ugly P1 hat 1 minus P1 hat over N1. P2 hat 1 minus P2 hat all over N2. And that ends up being, and this might be what you were saying, it's 0.318. If you take that away from 1, you get 0.682. And then you divide it by the sample size, which was 2,485. And then you add P2 hat, which is this guy, 0.226. Take that away from 1, you get 0.774, and divide that by 1488. So are you comfortable where the numbers from here, where they belong in the formula? In fact, isn't it only really these numbers and these ones, that number there doesn't come into it. So on my calculator, I have the big ugly square root to do. So here goes 0.318 times 0.682 divided by 2485 plus a 0.226 times a 0.774 divided by 1488, and that comes out to be 0.0143 and some other stuff. And they want the answer to 4 decimal places, which is good, because that's exactly what I rounded off to. And then they say, find the 90% confidence interval. That's the next piece of the puzzle. And the 90% is this guy up here, isn't it? Right. So what I'm going to do here is kind of cut some corners. I know what the difference is. They told me. So P1 take away P2 is 0.092 plus or minus 1.645 times the standard error. So that would be that guy. Are you comfortable about where this number came from, where this number came from, and where that guy came from? So that's now going to be 0.092, give or take that one. So we would go 1.645 times 0.0143, and the answer I get here is plus or minus 0.024. And if you take that guy away, we get 68, so 0.068. And if you add it, you get 0.116, which is what? 6% up to 11%. Okay, conclusion time. Is that evidence to prove that snorers have more heart issues than non-snorers? Right, the difference between the two is 6.8 up to 11.6. Is that evidence that the first is bigger than the second? Right. Now, if this data is validated by other researchers, it doesn't mean that snoring causes your heart attack. I strongly doubt that. But what it might be is that, we make this up, people who snore, maybe they tend to be more overweight than people who don't snore. And people who are overweight may have more heart issues than people who are not, right? So that might be the connecting factor. But if you were a doctor, couldn't you, when you're having a little conversation with your patient, say, do you snore a lot? And he says, yeah, I do. And he might think, that's one of those little flags. Maybe we should check, heart issues, because people who snore a lot seem to have a lot of heart issues, right? It's not that one's connecting the other, but it's a way of flagging, might be worth looking at. Are we good so far? Right, now, I only got to question 4. Can you trust me that question 5 and question 6 are pretty much the same? whiskey story, because what I want to do for the few minutes that we've got left is show you salt. Right. Which one shall I do? Let's do the one I've just got. Now, oh, before I forget, did I mention to you that our Zoom link dies today? We need a new Zoom link for next week. So I've made one, but I haven't had time to shoot it out. I'll probably shoot it out on something like Friday, or well, not Friday, Saturday or Sunday. I'll put it into Canvas as well. So when you turn up on Monday, remember, why is this link not working? Oh, that's right, that link stopped working on Friday. I need to use the new link. Right, are you looking at, I hope, question 4? Right, so we are going to hit the salt button and see what happens. And we are going to pick 2 sample proportion. Right. Did you notice the one I chose? 2 sample proportion. Now, you might think, oh, do I put in P1 hat? Nah, you don't even need to do that. You go here and you put in number of successes. Well, the snorers, if you think getting a heart attack is a success, there were 791 of them out of 2,485. So do you see I put in people who like whiskey, total number of people, right? And the second group was 337, and it was 1488. Are you comfortable with how you use what's called the raw data? Not the p hat value, but the 42 out of 50, the 9,000 out of 20 million, that number. Now you go down here and you click on confidence interval. You see that? Which kind of makes sense because that's what you want. Now, I don't want a 95, I want a 90, or I want a 99. Oops, not that one. I want a 99 or I want a 98, right? I think we wanted a 90, so let's return to the one that we wanted. And you go away, and you generate results. Now, they tell you lots of things, but the only numbers you're interested in for the interval are these 2 guys. So the lower limit is 0.068, which is exactly what I wrote down. And wouldn't the upper limit be 0.1158, whatever, right? Do you see? We've got our interval. Lower, upper. Easy to do, easy to check. And I think this is perfect timing. I'm getting good at this perfect timing.